Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, The Future, Mathematical Artificial Neural Nets. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the paper, A Logical Calculus of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to understand how the brain could produce highly complex patterns, by using many basic cells that are connected. They designed their system based on as they believed our brains work, and patterned it after the biological model of how neurons work with each other. The neural networks were growing, and in practice they took the name of artificial intelligence, displacing other methodologies and technologies that also generate artificial intelligence in the machines. Traditional artificial intelligence, based on artificial neural nets, ANN, and support vector machines, SVM, has concentrated its efforts on imitating the mental models of human beings in the recognition of patterns. Modeling efforts, coupled with today's great computational power, have enabled a great development in pattern recognition, definitively surpassing the human capacity for such activity. However, being a mental intelligence older than mathematics and creative, which has grown in the human being based on elements other than science, closer to empirical evidence, these characteristics are transferred to the scientific process of creating an artificial intelligence oriented to mental intelligence. Because of this, its growth has been slow than it would have been, if we had a scientific basis for mental intelligence. Within a nervous system, a neuron is an electrically excitable cell that fires electrical signals called action potentials through a neural network. The neuron is the main component of nervous tissue in all animals. Neurons communicate with other cells through synapses, specialized connections that commonly use minute amounts of chemical neurotransmitters, to pass the electrical signal from the presynaptic neuron to the target cell, across the synaptic gap. Neurons are highly specialized for the processing and transmission of cellular signals. Given their diversity of functions performed in different parts of the nervous system, there is a wide variety in their shape, size, and electrochemical properties. For instance, the soma of a neuron can vary from 4 to 100 micrometers in diameter. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. An artificial neural net is based on a collection of connected artificial neurons, which loosely model the neurons of a biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can send to neurons connected to it. The signal at a connection is a real number, and the output of each neuron is computed by some nonlinear function of the sum of its inputs. The connections are called edges. Neurons and edges typically have a weight that adjusts as learning proceeds. The weight increases or decreases the strength of the signal at a connection. Neurons may have a threshold such that a signal is sent only if the aggregate signal crosses the threshold. Defining parameters and topology is a combination of empirical work and scientific work, but there is no mathematical theory that must be respected. The algorithmic process is cyclical, and its convergence is based on the minimization of errors. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets, specialized in performing specific pattern recognition. For this, the basic patterns of ANNs are modified. Convolutional artificial neural nets. They correspond to ANN specialized in identifying certain types of patterns, such as images. The image presents an example of an ANN oriented to recognize images of numbers written freehand. The result is a discrete indicator associated to the number read. Generative Pre-trained Transformers, GPT, are a family of neural network models that uses the transformer architecture and is a key advancement in artificial intelligence, powering generative AI applications such as ChatGPT. GPT models give applications the ability to create human-like text and content, images, music, and more, and answer questions conversationally. Organizations across industries are using GPT models and generative AI for conda, text digesting, content generation, and search bots. But their ability to solve real decision-making problems, different from advanced pattern recognition, is minimal, if not nil. For many data scientists, data-oriented models are the only artificial intelligence out there. This includes academic teaching. This entails a problem of development of artificial intelligence, since many executives and managers not experts in AI think that the only artificial intelligence that exists is predictive. Then, it is applications such as ChatGPT, and the like, that will be considered the AI of the future. The displaced methodology is formal mathematical modeling using algebraic equations and/or differential equations. This is related to the use of mathematical programming, or optimization, to support decision-making. It is easy to show that in most companies, mathematical programming is not considered to produce knowledge, like the human. This is because decision-making does not concern researchers who promote artificial intelligence. Practitioners, perhaps fanatics, of traditional AI, have classified mathematical programming algorithms as the exact methods, not with the intention of highlighting them and promoting their learning. On the contrary, they disqualify them because in theory they cannot be used. But this is false. Mathematical artificial neural nets. Jesus Velasquez Bermudez creates a special neuron, which he calls mathematical artificial neuron oriented to support the creation of artificial brains, based on the structuring of mathematical artificial neural networks, which follow the mathematical structures derived from the atomization of mathematical systems and problems, following the methodologies of large-scale modeling, such as those developed by Danzig and Wolf, Benders, Van Roy and others. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, and for those of us who already work in high-complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. The greatest advantage of mathematical artificial neurons is that they represent clearly defined objects within a system, that communicate with each other through fully known mathematical laws, and that they comply with laws with transitivity and divisibility laws, in such a way that a system can be atomized, to the level of knowledge that the scientist on duty has. More complex methodologies, such as cross-decomposition, generate cross-structures like the real structures of neocortex. Everything indicates that the structure, and joint functioning of the neocortex and hypothalamus, is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. In 1983, Tony Van Roy created the cross-decomposition approach, to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. When simple problem division methodologies are applied, verticalized structures are obtained, that ignore the transfer of horizontal communication. That is, use only Bender's theory, or only Lagrangian relaxation. More complex methodologies, such as cross-decomposition, generate cross-structures like the real structures of neocortex. The structures that can be produced, can have any topology, like neocortical structures. However, it should be noted that while in neuroscientific studies, topology is not clearly explained, but in the case of large-scale mathematical structures, topology is defined by mathematics, and not by human interpretation. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. They continuously produce information, and it is stored in the artificial hippocampus, an intelligent database on disk, or in RAM, which can be accessed in the next conversation of all robots. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. They continuously produce information. Lagrange's work is the basis of a universal mathematical language for robots, based on mathematical programming. An artificial hypothalamus is a network of mathematical artificial neurons. Each of them represents a system or subsystem. The difference with large-scale methodologies is that the solution is visualized as specialized communications between mathematical problems, while in the artificial hypothalamus the process is cooperative based on autonomy, distributed, and real-time processing. In addition, there is a standardized language for communications between mathematical artificial neurons. Any type of organization can be represented following these principles. The case of a poultry production system is presented. The system has been divided into 6 subsystems, which together make up the poultry production system. The actual state of the evolution of artificial intelligence is the artificial brains based in mathematical neuron swarms. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence, to generate mathematical programming solutions, using the models that traditionally make up a decision support system. The new way of mathematics is directly related to the parallel thinking, and today it can be said that, like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Enrique Krauss, in the prologue of Cyber Leviathan, wrote, "Artificial intelligence is restructuring human life in unimaginable ways. With it, certain occupations in which we consider human intellectual and emotional capacity indispensable will end up becoming extinct, replaced by incredibly complex systems capable of emulating it. This makes our situation very different from that of 2 centuries ago. This time the machine will be able to completely replace the human being with his physical and cognitive abilities, and with this he could inevitably deprive a very high percentage of the population of work experience, which has been an essential element in human identity. Thank you very much for your attention.